Awesome. Welcome everyone to the community meeting for March. So today we have a presentation by Rob. He's going to talk about some of the quantization work that he's been doing in Torch-MLIR, taking models, I believe, through Onyx, and then quantizing things. So I'm really interested in this because my team has been working with quantized models as well, and so figuring out the study for Torch-MLIR will be very useful. But before that, a quick reminder about our different meetings. So this is the community meeting. It happens once a month on the first Monday of every month at 9 a.m. Pacific time. And usually we have someone present about some of the big feature work happening in Torch-MLIR. And then every other Monday we have developer hours, which is, there's no agenda, it's not recorded, and you can just come and ask questions about pretty much anything. And lastly, there's also office hours every Thursday, and those are hosted by me from 8:30 to 9:30 a.m. Pacific time. And the best place to sort of stay up to date on everything is through Discord, so all the links are in the slides. Now, a few statistics. So this is since December 1st, and I think we've hit sort of a record number of commits in the last 3 months that we've never seen any other time in Torch-MLIR. So exciting time. Yeah, thank you all the contributors who have been working really hard on this. It's really nice to see the project grow. And with that, I'll hand it over to Rob to present. I think you should be able to control the slides, but let me know if...
I should be able to do the thing of actually finding the right window. This one. Yeah, there you go. Same slideshow, easier to hand over this way.
Okay, yeah, that works.
Yeah, it's just easy this way. So for sort of covering this, we ended up wanting to actually start getting proper end-to-end workflow for quantized models that are a little more clearly done. And one of those standard mechanisms used is called QDQ quantization. This is what's referred to in Torch that way. Sometimes called fake quantization within TensorFlow. And for the quick 101 on quantization, turns out that if you process fewer bits, things go faster. And so the main goal in trying to use quantization is you can take something like a 32-bit float, you can decrease it down to 8 bits. It's like bfloat where you have like 16-bit quantization, you can still reduce down to 8-bit, and it ends up having more than a super linear effect. So it's more than twice as, if it's half the bits, it's more than twice as fast. Has to do with how the tiling and actually data throughput works. And so in this, you typically apply an offset or a scale, an offset, and a clamp, and then you convert the type to a limited integer type, and then you do the operation on that. And then depending on following operations, you might dequantize it or requantize it. So in the case of QDQ quantization, QDQ stands for quant dequant. You're actually representing the main model, or the model gets handed to you in this form where you have the value coming in as a floating point value. You then quantize it to whatever bit depth you're going to do. So in this case, it would be I8. And then you dequantize it back before feeding it into the actual dense operation. This feels like it's counterintuitive, like this isn't actually quantizing it, it's just converting it and bounding it so that the actual operation would have the same numerical outputs. But there are a few reasons why this is done. One case is that when you're often quantizing these models, you'll slowly remove the number of bits that you have so that you can adaptively quantize it and you won't have as large of a loss. But the main reason why you see this more often in things like PyTorch is that the way these models are quantized is that you will have your whole model written and running on floating point, and then you'll run a post-quantization tool on it that inserts these quant dequants surrounding each dense operation. So the sort of 3-stage approach is train it as a fully floating point model, insert an initial set of ops that'll grab statistics on both the weights, inputs, and outputs, so it knows what the preferred quantization range on the input and output is, And then using those, you can apply these new quant dequants with a scale and 0 point that should produce reasonable results. This can include including the fake quantization and slowly subtracting bits and doing additional training steps to handle quantization. What this benefit is that this actually carries the quantization information on these op parameters. So you can think of it as this quantize per tensor knows what the length and scale is, and then when dequantize executes, it operates on this quantized int, knowing that there's that previous information carried. So really what we want to do, and what we do, is we have a new fuse quantize pass that says, okay, well, if we know that we have a mapmul operator, and we know that the inputs are coming from dequantization, we can remove those operations and directly wire the qint type in. Assuming that the dequantize operation is coming from an operation that is carrying the 0 point and scale information, we can then say, well, we will operate on this with mapmul, knowing that those parents each have a scale and 0 point that we can directly operate with. So we essentially just strike them out, rewire in, and have now a mapmul operating on this much narrower type. So once it's actually fused, you have this mapmul, you have a quantized per tensor feeding in, and now you can update what the output type is. So note previously we were still operating and producing a float 32 type. Well, when you're actually running this dense op, you don't actually want to accumulate within a floating point value. Reasons for this are, for one, if you know that you have integers coming in, converting them to floating point is actually just losing you precision. The mantissa and exponent combination isn't worth it when you know you're just multiplying some integers and adding them together. And so what you can do is say, well, I know what the scale and the 0 point are on each of my inputs. I can now be aware of these values when generating this int, and then dequantize it as it's that type. So you'll see through the sequence, we have, again, the two quantized per tensors. We have the mapmul operation, and then we pull the int representation out. So we basically know that we're generating assigned int 32. For context, typically when you have one of these dense operations, they only take the 0 points, and the output always has a 0 point to 0. The scale will be the product of the two previous scales, at which point we can take that, regenerate a quant 32 type, so a qint 32, and now we can dequantize that to the F32 variant. This is true for most of any like multiply sum operators. You can think about doing this for other operations as well. The convolutions, same thing. You would multiply the scales. If you ran something like a max pool, the scale doesn't change. If you do something like an average pool, I believe the scale doesn't change, but you have to adjust for the scale, the fact that you're accumulating all of them. But this lets you now take this large qint 8 type, get it to a qint 32, and then restore it back out to an F32 type. And effectively, we can now focus on only the part that matters, because everything else, these like quantize per tensor and dequantize and make per tensor, those are just standard element-wise operations. We have lowerings for them. It's essentially convert to or from F32 and apply scales on the floating point side, along with applying the appropriate offset. And what we really want to focus in on now is that mapmul. So you can think of it as, I have a mapmul, I have two qint 8 types, which the difference between a qint 8 and an int 8 is that it basically indicates that there's additional scale and 0 point components. And this output type of qint 32, which is really just what that accumulated I32 is going to be. And it turns out that this maps basically identically to something already in linalg. So to reinterpret it slightly simpler way, mapmul happening with a bunch of signed in dates. They have some scaling information attached along with some 0 point fed into a mapmul, and then we have the component come out. And for linalg, the way that we represent mapmuls is that you have your raw integer types come in along with an additional 0 point offset. This way you can either apply the 0 point offset within the accumulator loop, or you can post correct for it, which is what I think linalg does today, because it's slightly more efficient. And so replacing this with the existing linalg mapmul op you can actually just say, okay, well, I'm going to route these 0-point values in instead. I can now perform a quantized mapmol on those components. And then linalg will handle all of the special 0-point correction. And what we're able to do is just route it through. The whole idea with each of these stages is that we can slowly first take this quant-dequant representation, convert it to just a quant with a quantized representation, then go and map that to the existing linalg op. At this period of time, we have it working with sort of the linalg mapmol and convolution operators, namely the sample model that we were wanting to just verify that we could get this working was ResNet, and it's running end-to-end fully quantized. And yeah, like we're able to represent it. There is still a decent amount of work that needs to be done. There's multiple mapmol operations and multiple convolutions, so we have to still support the additional fusing and a handful of lowerings. But for most of them, we actually have this working now end to end. The only other parts that are still TBD are activations are typically still applied in F32. So if we go back to the starting representation, we have this value come in, and it would be quantized, then dequantized, then fed into the dense operation coming out as an F32. The activation would then be happening on that F32. For some, we should be able to switch it. So basically perform the activation in whatever the accumulator type of an A10 mapmol is, or A10 convolution. But for some, this isn't going to be as straightforward. For instance, you'll lose numerical precision if you run it on something like a 10H activation layer or a sigmoid or anything that's like a non-linear activation function or non sort of Heaviside style activation function. But yeah, that's basically the main run through. It turns out it didn't require too much work to plumb through. It was mainly about just getting this routed correctly into mapmol and then ensuring that our existing linear operation had a mechanism to map to the existing linalg ops, which are, I think, just linalg mapmol and linalg convolution variants that support quantized types. So yeah, open to any questions if folks have any. It was a little bit of a quick run through. Sure, Matthias?
Hi, that looks really good. Thank you. My first question is, how much of this is already upstream?
Like in Torch-MLIR?
Yes.
All of this is currently upstream. We already committed the majority of this, so the whole process of going from it, it was just mainly the addition of a new quantized fuse pass, which is already part of the pipeline, and the lowering to linalg, quantized linalg. One of the things that's kind of interesting to note about this is that this is kind of our only path, I think, that we have for quantized models coming out, or at least one of the only. I think you can do raw integer type mapmol still, because I think that's how we're getting Llama and a few others out. But currently, FX does not let you trace quantized types, and so there's no other way to generate these QInt operations other than basically fusing them in. Well, tracing it, then inserting them via an FX tool, and then fusing together. But yeah, the whole thing's upstream.
Okay, sounds good. And my second question is, I'm interested in sub 8-bit quantization, which some quantizers represent like a QC DQ. So you have a quantize and a clamp node and then a dequantized node. I wonder what you think about how those could be supported in this flow.
So it was a quantized node, and then what node?
A clamp. So you like clamp it, for example, to 0 to 8, and then you get like a 4-bit integer representation in a sense.
Okay. So the main issue I can see with it right now is that we have to have some representation that we know that we can say, like, okay, this is like the 0-point in scale. If you insert, like you do the quantization clamp and then dequant, the quant information ends up being trapped behind the clamp. So obviously problematic because, like, I'm assuming you're doing this because you want to do 4-bit and there's no QInt 4 type. I would say that most likely we would either have to be able to pass additional attributes or like attach some additional information to the quantize type to indicate that the value is clamped and then apply the clamp earlier in the process. But there's at least some engineering work that have to be done there to figure out a consistent way to pass it. Main reason for this is that we predominantly use two operations in order to attach the quantized scale information, which is either make per tensor quantized tensor, which basically says I have this int date, I want to attach some scale and 0 point information, or we use the quantize op. The one option is just basically doing a little bit of special work for clamp if it's important enough, where we can detect the clamp and then check the parent above it and see if that's a make per tensor or a quant per tensor, and then pull the values out of it. So this it's feasible to be done, I think. I don't think it'll be too bad to add.
Okay, thanks.
Abhishek?
Yeah. So I had a question, like, can this now be lowered to like a TOSA or something?
Yeah, so there'd have to be a little bit of work done on the torch to TOSA lowering, but it should be able to. TOSA uses a similar representation where it has that 0 points and scale information. So we would just we would use the same pass that we're using to fuse the torch types, and then we would just have to make sure it updates so that it invokes the TOSA version with scale and 0 point. But I can't see any reason why it shouldn't work. I think the only issue I can see is you have to make sure that the 0 point and scale values are foldable. With the lowering to linal, that's not a firm requirement. They can be just scalars computed at runtime. But with TOSA, I believe they're attributes. This wouldn't be like a major issue for most models. And the worst case scenario is that for cases where it could be supported, we'd have to make sure that the torch folders are up to snuff for constant folding it. But it should be routable. I think like one patch would be all that's needed, and we can get the matmul and convolution operators hooked up on TOSA side.
Okay. So as of now, only matmul and convolution layers are supported for this quantization, right?
Correct. Yeah. So this supports both convolution and matmul. We're planning on doing the work to support a few other operations because things like average pool and max pool, and even like having basic activations happening in quantized space is good. I think the only other quirk that we have to make sure that we handle is we do this quant dequant, and this could result in like things dequantizing and then requantizing to the same range. So there's still some optimizations required there. And if you know that you're dequantizing and requantizing, even if you're doing it to different scale and 0 point, you can actually directly do all of the conversions in integer math. So this is what TOSA actually specifically does, is the rescales are done purely in integer operations. So you'd have to do a little bit of a different rewrite where when you see a dequantize operation, you check to see if the parent is a quantize, or if you see a quantize operation, if the parent is a dequantize, you can actually take those two ops and turn them into a single TOSA rescale. So there's some like little quirks that'll be different, but
okay. Thank you.
problem. Ramiro.
Yeah, so yeah, I have a question. So you mentioned that this is like the sort of path for post-training quantization is you first have an algorithm that computes the right, 0 points and ranges for things and so on for all the different tensors. And this is sort of what happens after, right? How did you do it for ResNet? So like, do you have some algorithm you've been using to compute these things?
So I think the ResNet model we were actually coming from was an existing Onyx one. So we used the Onyx to torch path to generate the equivalent torch operations, and it was already quantized, so it was represented with this QDQ mechanism. But if we want to talk about the ones coming directly from Torch, I believe the path that ExecuTorch uses, it has a quantization library where you feed a model in that's already, I mean, it's usually not quantized, but it actually automatically both inserts the additional trackers, runs it with some sample data you give it, it then tweaks the values a little bit. I think there's like a tiny bit of backprop, but most of it is just knowing like where can it afford to lose precision. And then it just determines those scales and then inserts the values with the actual scale offs. What's a little unusual is that you get this model and all of the weights are still stored in F32. So you have to actually constant propagate the, like if you want to actually make the model swallow, you have to constant propagate the quantize operation into your weights so that they're actually in a quantized, more compressed form. But that's not too complex to do. Yeah, for the most part, it's just the existing tooling that exists within main Torch that will generate it, and that's all handled like pre-Torch-MLIR.
Gotcha.
Mhm. Yeah, and so like for the coming from Onyx work, like Onyx has some amount of quantized value representation. I forget exactly how they do it. It's been a while since I looked at that. But the neat thing about it is because they are represented sort of natively as quantized types, we're able to take them, lower them to the QDQ representation, which basically defuses the F32 from it, and then it can fuse it back in as a post part, or you can import it already prefused technically. I think they have like special quant ones where you can do it prefused. You just have to make sure it's compatible with how the Torch to Linalg path works.
Mm-hmm. Yeah, the path I experimented with was using a library called GPTQ. But so what it does is it takes your PyTorch model and then replaces some of the layers, like the linear layers, with their own custom written quantized versions. But then the only way that we were able to get it into Torch-MLIR was through a path that basically keeps all the matmols in floating point. It basically stores all the weights as like integer tensors, but then it dequantized before doing the matmol, and then gets the output as an F16.
Yeah,
so that,
and
yeah.
the side effect of this is the fusing aspect is then in turn under doing that where you're like then pulling it in as again a quantized type just with a fixed information. Yeah, it's we saw a lot of this like 5 years ago, 6 years ago with Torch-MLIR, or not Torch-MLIR, TensorFlow and TF-Lite, where a lot of it ends up being that you insert these, like everything's happening in floating point. It never is an integer, or at least never was 5 years ago. And then it was purely TF-Lite could recognize like, oh, I see a fake quant feeding into this thing. I can convert that to integers. And so it just looked for this pattern of like dense op with these surrounding fake quants. And then it just removed all of them and inserted the quantize operation. And then in turn, it could also see that if you had like the quant, dequant quant, it could just be like, this is an inverse operation. I can throw this away because it's like non-value changing.
Yeah. Cool. Yeah, my other question was, in terms of the design, do you see any sort of like the pros and cons of going using ops to capture quantized information versus the types themselves, which I think was a design that had been proposed at some point?
So it would be nicer if the qint type actually had appended information. Now the downside of that is I've seen where like, appending the quantized information, like having two values is not a big deal for a single type. When you start getting to like per channel quantization, having like 500, floating point scales and a bunch of 0-point scales attached to like a single type is a little bit gross. It would be nicer to have it appended, but the op carrying semantics happen to match closer to what Linalg does anyway. Like this operation is actually saying like, well, the 0-point, the scale are a value in the operation, so having them plumbed in. I think the biggest issue is that it's side channeled. So, if A10 matmul had optional parameters that were like, oh, here's the 0-point, here's the scale, and they can get fed in, maps closer to Linalg, maps closer to what the actual computation is, and then you would just have ops computing these appropriately. But we're inheriting something where quantized types literally have a little lookup table sitting somewhere in Torch that says, okay, here's the scale, here's the floating point. And so when I say like matmul on a qint8, it literally knows to go look at a table somewhere and pull that information, which doesn't work when you're trying to generate a side channel information. You'd have to then like insert a table and then have a way of mapping your specific outputted type to the unique value in a table, and it's kind of gross. I tend to be a bigger fan of the ops carry, or the ops being used to carry the semantics. But it's certainly not optimal for like this make per tensor quantized value, because let's say that you're wanting to do a bunch of math on a set of quantized tensors, so quantize 2 of them and then add them together and get like an N32 out of it and do a bunch of math in quantized value. You could see something like this happening for like an LSTM cell, for instance. It'd be nicer to do it that way, but the problem is that every time you'd have to attach the quantization information and detach it, and now you have all of these dequants just designed to attach that information onto it. Which is a little gross for propagating it and making sure that you update everything correctly, but unfortunately, like that would be the world that we live in. Our one benefit right now is it doesn't appear that anyone's really looking to do that as much anymore. LSTMs are far less common today than they were 6 years ago, so should give us time to like help shore up that story and make sure that the stuff that matters is quantized in the right way.
Makes sense. Cool.
Cool.
Yeah, those were all the questions I had. I don't know if people have other questions.
I think we're all good. I think you get to take the take the form back from your own. So I will click that.
Let's see. Okay. All right. Well, yeah. Thank you so much for the presentation. This is really, really useful work. And yeah, now we just have, our monthly Torch-MLIR health checkup. There have been a lot of, so normally we ask this question every month to see if people have issues with CI or the sort of flow, developer flow in Torch-MLIR, and we never get any issues in the meeting. But there have been some really nice changes, I think, for the CI since the last community meeting. So Stella simplified the CI quite a bit. Now we have like really fast, for example, linting checks so that you don't have to wait for, a 20-minute CI workflow to finish before you know that you didn't, indent a line properly. So that's quite nice. And I think it's just a lot faster. So hopefully people are having a good experience with that. If not, do raise those issues on Discord or GitHub if the CI is not working properly. But
I like for the linting part, actually, the documentation is not very clear as to how to run lints on local system rather than pushing to the CI first, pushing as a PR and running to the CI. So if we can get a documentation where we know how to lint beforehand, then it would be, I guess, better.
That's a really good point. Yeah, I can add something.
Do you have Git Clang format installed?
Yeah, I got to Clang format installed, but like it took me some time to figure this out. Like I had to go and check the CIs and stuff on how it was working and to replicate it. So I guess it was, what you can say, a bit of a hassle. Had it been documentation, it would have been really quick. You just copy the command and yeah.
Yeah, we can try to add some line about it. Have like a check pre-submits or recommended things to do before submitting to the CI queue.
Yeah. Yeah, the Git Clang format is definitely not intuitive at first. But yeah, we can add documentation for that. Awesome. Are there any other questions?
Like maybe a Git hook can help. Like every time you post something, you just automatically just runs some sort of lint checker, something like that type. I guess that would be useful.
Yeah, I know so I don't have any experience with this, but I know some people have more sophisticated Git flows. I could probably ask around and see if someone knows how to add something like that, a hook to Git. But yeah, that would be quite useful. I did see a few PRs that were sort of waiting for the CI to tell them how to format changes, and that's definitely not the flow we want for people. Any other questions? All right. Well, thank you everyone for coming. Thank you, Rob, for the great presentation. And have a good rest of your day.
Bye.